Hello everybody. In this video we're going to be looking at the solutions to the college prep sound homework problems 11 through 15. Let's start with problem number 11. A vertical tube with a tap at the base is filled with water and a tuning fork vibrates over its mouth. As the water level is lowered in the tube, resonance is heard when the water level has dropped 17 centimeters, and again after 49 centimeters of distance exists from the water to the top of the tube. What is the frequency of the tuning fork? So this is a closed tube. We know that it is a closed tube because there is water at the base. So the bottom of the tube with the water is going to be closed and the top of it is open to air. So because this is a closed tube, I know that there is 1/2 of a wavelength between my points of resonance, or between my resonant frequencies is another way of saying that. So I have one resonant frequency at 17 centimeters. We can call that our fundamental harmonic or our fundamental frequency. We have our other harmonic frequency at 49 centimeters. Remember that points of resonance are where we have our harmonic frequencies. So I have one harmonic at 17 centimeters and I have another harmonic at 49 centimeters. The distance between those represents half a wavelength. So I can say that the distance between 49 centimeters and 17 centimeters is equal to 32 centimeters, which is equal to 0.32 meters. I do have to convert this to meters. And I know that 0.32 meters is equal to 1/2 of a wavelength, because that's the distance between my 2 points of resonance or my 2 harmonic frequencies. So now to find the wavelength from this equation, I simply take 0.32 meters, multiply that by 2, that will give me a wavelength of 0.64 meters. Now I can find the frequency of the tuning fork, because I know that the wave speed is going to be 343 meters per second. I don't specify a temperature here, so we're going to assume a room temperature of 20 degrees Celsius, which means my temperature at 20 degrees Celsius is always going to be 343 meters per second. So to solve for the frequency, I take my wave speed formula. Velocity equals frequency times wavelength. Solve that for frequency. I have frequency is going to equal the wavelength frequency is going to equal the velocity divided by the wavelength. So 343 meters per second divided by 0.64 meters will give me a frequency of 540 hertz. Problem 12. The auditory canal leading to the eardrum is a closed pipe that is 3.0 centimeters long. Find the approximate value, ignoring end correction, of the lowest resonant frequency. First of all, let me just mention this. We're ignoring something called end correction. If we were in school, I'd be explaining what end correction is, but we're just going to ignore it, and we're not even going to touch upon it for any of the things that we are going to do. Basically, what that means is that when you have air vibrating in a tube, part of the air molecules just outside of the tube will also vibrate, and we need to correct that. It kind of extends the length of the tube artificially a little bit. So there's a little calculation, a little correction that we typically have to do for that, but we're going to ignore that. You don't have to worry about it. It's not going to be on the test. You're good. So we want to find the lowest resonant frequency. And we know the length of the tube, and the length of the tube is 3.0 centimeters. And I know I have to convert that to meters. So that's going to be 0.030 meters. Now I know because it is a closed tube, I know from the PowerPoint that the wavelength for the fundamental frequency is 4 times the length of the pipe. We went over that in the PowerPoint. So I can now rearrange this to say that the length of the tube is equal to the wavelength divided by 4. And I know that the wavelength is equal to the velocity or the speed of the sound wave divided by its frequency. So if I take this and I swap it out for wavelength there, I am going to have the frequency equals the velocity divided by 4 times the length, which is again my formula for harmonic frequencies in a closed tube. We don't have the n in there because n equals 1. We're dealing with the fundamental frequency for this one, so we just ignore the n. So now I can solve for my frequency, and the frequency is going to be my speed of the sound wave, which again I don't specify an air temperature, so we're assuming 20 degrees Celsius, and the speed of sound at 20 degrees Celsius is 343 meters per second, divided by 4 times the length of my tube, or 0.030 meters. Do that math out, and I should get a frequency of 2,858 hertz, or 2,900 hertz, to two significant figures. Problem 13. If you hold a 1.2 meter aluminum rod in the center and hit one end of it with a hammer, it will oscillate like an open pipe. Antinodes of pressure correspond to nodes of molecular motion, so there is a pressure antinode in the center of the bar. The speed of sound in aluminum is 5,150 meters per second. What would be the bar's lowest frequency of oscillation? So just to recap what nodes and antinodes are, I'm going to try and draw this here. I'm not going to draw it well, so bear with me. All right, if I have a pressure wave, it's going to look like this, and let me just draw it kind of like this. All right, well, hey, that's not so bad. All right, if I have a pressure wave, and it looks something like that, I know where the displacement or the combined wave is at a minimum here, where the two things cross each other, where the two waves cross each other. That is a node. And where I have my maximum displacement here, that is the antinode. So just kind of keep that in mind. All right, let's take a look and see what we're given here. I know the length of the pipe is 1.2 meters, and the speed of the sound in aluminum is 5,150 meters per second. I know the length of the rod is equal to 1/2 of a wavelength. And remember, I know that again from the PowerPoint. In an open tube, I know that the wavelength for my fundamental frequency is equal to 2 times the length of the pipe. That's right out of the PowerPoint. So again, if I want to solve this for length, divide everything by 2, I know that the length is going to equal the length of the tube is going to equal the wavelength divided by 2. So that's where we can get the rod length is equal to 1/2 of a wavelength. So 1/2 of, so it's 1/2 of, I'm going to try this again. I'm totally screwing this up, and I don't want to redo all these drawings again. So normally I would have stopped this and done it over, but I'm going to keep going here. Because the rod length is equal to 1/2 of a wavelength, the wavelength is going to equal 2 times the length of the rod. That's what I was trying to say. So 1.2 meters times 2 is going to be 2.4 meters. That's my wavelength. So now I can find the frequency because I have the wavelength and I have the wave speed. And I know the frequency is equal to the wave speed divided by the wavelength. So 5,150 meters per second divided by 2.4 meters will give me a frequency of 2,145 hertz, or 2,100 hertz. Problem 14. One tuning fork has a 445 hertz pitch. When a second fork is struck, beat notes occur with a frequency of 3 hertz. What are the two possible frequencies of the second fork? So the frequency of my first fork is 445 hertz. It's telling me that beats occur every 3 hertz. And remember, the beats are the intervals between frequencies. So I know that if my beat is 3 hertz, that my second fork has to be either 3 hertz above the first one or 3 hertz below the first one. So 445 hertz plus 3 hertz will give me a possible frequency of 448 hertz, and 445 hertz minus 3 hertz will give me a possible frequency of 442 hertz. So the second fork has to be one of those two frequencies. Problem 15. A flute acts as an open pipe. If a flute sounds a note with a 370 hertz pitch, what are the frequencies of the second, third, and fourth harmonics of this pitch? So my fundamental frequency is 370 hertz, and we're being asked to find the second, third, and fourth harmonics. So I know because this is an open pipe, I know that the second harmonic frequency is going to equal 2 times the fundamental frequency. So 2 times 370 hertz is going to be 740 hertz. The third harmonic frequency is going to equal 3 times my fundamental frequency. So 3 times 370 hertz is going to equal 1100 hertz. And my fourth harmonic is going to equal 4 times my fundamental frequency. So 4 times 370 hertz is equal to 1500 hertz.